Hey there, everybody. Welcome back to our series on Introductory Econometrics. In this video, we'll be continuing from the last presentation, continuing our discussion of specification and the estimated regression equation. In this video, we're going to continue that specification question, and this time we'll be talking about functional form. And by functional form, what we mean by it is what is the relationship of how changes in our independent variable, how we expect those changes to impact the estimated value of our dependent variable. So some things over here. So we'll start talking about the use and interpretation of the constant term, alternative functional forms, right? And I'll go through several of those. Then we'll talk a little bit about lagging independent variables and then slope dummy variables. Okay, starting with the constant term. So, we sort of, thus far, right, we've sort of always kind of, we've run our regressions using a constant term, right? And then we've introduced it into all of our equations, right? It's sort of been there in the background, but we've never really talked about what it is. Now, mathematically, it's very straightforward, right? The constant term is simply the value of our dependent variable when all of our independent variables are 0, right? Okay, but economically, and of course in econometrics, it has a deeper interpretation than that. The value of our independent variable that comes from factors outside of the parameters that we're trying to estimate. Okay, now that's a sort of complicated way of saying it's things that impact our dependent variable that we're not talking about at all. Let's say that we were regressing sort of a fishermen's nets and fish caught, right? So let's say we wanted to explain fish caught as a function of the number of nets that a fisherman puts out, right? Which would be sensible, right? How many nets should I put out? What's the marginal value added, so on and so forth. It's a reasonable research question, although it seems a little silly. And let's say that there are other people catching fish, right? Like maybe there's a lawyer who just happens to go out fishing one day, has no net, uses a line, rod and line, and catches a bunch of fish. Well, that has nothing to do with our model, yet positive fish were caught on that day, right? So if our fishermen with nets went out and didn't use any nets and didn't catch any fish, just went out for a joyride that day, our data is going to show positive fish were caught. Well, that's because they weren't caught by a fisherman. They weren't caught with nets, right? Okay, so that's what we mean when we say sort of that there's data that's outside of the parameters that we're considering, right? Lawyers enjoy fishing with reels are not part of anything we're trying to explain, yet fish are caught that way. Failure to include a constant term in most cases, right, the vast majority of cases, it's going to violate our classical assumptions. And the reasons are over here, right? So if we have that sort of lawyer with the rod and reel catching fish, right, then our explaining fish caught only with fishermen and nets is right. It's gonna, that estimate's going to be biased. Our estimator on nets is going to be biased because there are fish caught without nets, and so our prediction of how many fish nets catch is now wrong, right? It's biased high. So this constant term, as it says over here, along with the error term, right, also sort of scoops up these random disturbances. Okay, so even in a well-specified model, the right variables, the right functional form, right, this constant term scoops up this sort of information that's outside of the parameters that we're trying to understand. Now, so far, with exception of a small example here or there, all of our work so far has been linear, right? So like the equation that we see, well, here, I'll use the mouse. I guess maybe that works better than I thought. Okay, so like here, right? And in these sort of simple linear representations, right, we're able to interpret the beta coefficient just pretty much as it says. So if this beta is 0.5, that means that a change here of 1 is going to change this by 0.5. Okay, this is linear form. And if we expect the x variable to impact the y variable in a constant manner, that is, every time this x happens, the exact amount of y happens over and over again, right? Well, then that's entirely appropriate, right? And in fact, to do anything else would be inappropriate, right? But what if that's not the case? What if we expect maybe the first changes in x, so if x changes from like 0 to 1, we expect a big change in y. But then as x increases, it sort of tapers off. Like maybe the number of bathrooms a home has on a home price, right? If a home has 0 bathrooms, and then you change it to 1 bathroom, probably has a really big impact on the home price. And then as you add a second bathroom, it probably has a pretty big impact too, but maybe not as much as the first one. And the third one also has an impact, but not as big as the second or the first one, and fourth, and so on and so forth. In other words, the relationship sort of increases at a decreasing rate. Well, if that's the case and we're using this simple linear form, then our estimate of beta 1 is going to be incorrect, right? And so we need to, so how is it going to be incorrect? Well, in that case, we're going to underestimate the value of the first bathroom, and we're going to overestimate the value of the fourth, fifth, and sixth bathroom. Okay, right? Okay, so when that's the case, how do we sort of fix this? How do we make our estimated, or how do we make our hypothesized relationship meet that expectation? In this case, we might use what's called a double log form. Okay, and this is over there. So if we expect the true relationship to be something like this, okay, which would be consistent with what we were just saying, and I'll draw you some pictures on the next slide. Okay, right? That is, we expect the x to have this sort of exponential relationship. Now, in the example I just gave, it would be the exponent would be less than 1, right? But okay, it could be the other way too. Okay, so we expect our x1 to have some kind of exponential relationship to changes in y1. Okay, well, we can rewrite that relationship in this way, where ln is standard for the natural log. Okay, and what we have now is mathematically, this is the same as this. Okay, so by doing this conversion to this sort of natural log form, where we've got a natural log here of the y and a natural log of the x. Okay, so double log, 1, 2, double. Okay, mathematically this is the same thing. Now we're gonna play around with this a little bit in eViews in the companion video to this, right? So I can kind of show you what's going on here. But when we do this, when we expect these sort of relationships like this, and we design our estimated regression in this way, right? A difficulty that pops up is that we can't interpret that beta 1 in the same way that we did before, right? So the value of this beta 1 is going to be an elasticity or a percentage change now. Okay, and again, it's maybe hard to understand that now. I'll show you when we do it in eViews exactly how that comes out. But this is going to show you the percentage change in y that can be expected given changes in x. Okay, here's some examples of where we would use double log forms. I'm going to move myself just a smidge, right? So you can see all three of those. And so here, in the first case is where our estimated beta is going to be greater than 1, okay, or our exponent is greater than 1, right? And then the second one is where our beta is going to fall between 0 and 1. So, right, so like if beta is 0.11, right, it suggests this kind of form, the one in the middle there. If beta were like 2, right, it'd be squared, right, that sort of look like that, right? And if beta is less than 0, right, then we get this sort of form like that, okay? Second up then is the semilog form. So this is used when some, but not all of the independent or dependent variables are expressed in terms of their natural logs. Okay, so maybe we have a hypothesized relationship where we think some x variables are going to be linear, right? The relationship between x and y is going to be linear. So every time they go up by 1, maybe y goes up by 2, always, right? It's linear. But some of our variables have this, logarithmic style relationship, okay, or exponential style relationship, okay. Then in that case, we use the semilog form, which is written like this. Okay, so we notice we only now have the log style relationship in one of our x variables. Okay, and in this case, right, we can interpret it beta 1, right, as an elasticity, and beta 2 in the standard linear manner. Okay, so also can be very useful when you have sort of different variety of relationships. Now, before we go any further, I want to say something to make sure that I don't forget it, right? If we're running a regression, one natural log of y and then other just straight y, right? It's important to remember that we can't compare those regression outputs sort of one-to-one in terms of what's better, right? So because we're looking at different dependent variables in each case, our output, regression output, including our r squared, is no longer appropriate for direct comparisons. Anytime you're comparing this regression output from that regression output, okay, it has to be the case, among other things, but it has to be the case that your dependent variable is the same. Otherwise, you're comparing apples and oranges. Okay. The third functional form that we want to discuss here today is the polynomial form, which is, it says here, used when the slope of a relationship is expected to depend upon the level of the variable itself. So, for example, like if you remember your basic microeconomics, like most cost curves, like average cost curves or most marginal cost curves, right? They sort of generally go down and then they come back up like a bowl or something like that, right? Okay. You know, mathematically, these are polynomial functions, okay? And there are many, maybe infinite, probably, you know, right now mathematicians going, there's infinite, right? Okay, I'm not a mathematician, I'm an economist, so always I'm concerned about what math can do for me, not math itself. But in econometrics, certainly there are many polynomial forms that we utilize to estimate different types of relationships. Okay, so you know, over here I give just one example, and then on the next slide I'm going to show you some pictures, right? Okay, so here what we're doing, right? You'll notice something about this that we've not done before. There are two x1s. Okay, there's a beta 1 associated with this x1, and there's a beta 2 associated with this squared value of x1. And this over here, right, just to illustrate other stuff. So here we're regressing both the linear relationship of x1 to y as well as the squared relationship of x1 to y. Now there's a lot of reasons why we might do something like that. Just two off the top of my head that I can think of is we may be concerned with sort of like an absolute value style thing, right? So we don't care whether its variations are plus or minus, right? We just, okay, well then square it, right? Because negatives times negatives are positives, right? Okay, so great. Or we may wish to understand whether this is a linear relationship or it is a nonlinear relationship. Okay, so here's just a couple examples, right? So you've seen that one before, right? Here, right? So you can see that you know, this is a very unusual one. So like up, right, and over, up, and back down. Okay, this sort of form right here. So any of these can be applied, can be rewritten in a linear form that now becomes acceptable to utilize our linear regression process that we're outlining here. Right. All right, now when you're using these polynomial forms, which again, I mean, you can kind of see that it's not uncommon, right, to do. So here's one, you know, from the previous, right? So here I've got a log style relationship, right? And then you'll notice I've got x1 here and x1 here, the squared relationship here, and the linear relationship here. It suggests that the growth rate of y is positive but at a decreasing rate, right? So if we run that, right, and we get beta 1 to be positive and beta 2 comes out to be negative, right, it's an indicator to us that that relationship is probably something like this, right? So increasing at a decreasing rate. And that sort of test run, right, then suggests to us that, you know, either a semi-log or a double log functional form would likely be more appropriate in this case. And so we can use these in this case polynomial relationships to to sort of figure out, what the functional form, the true functional form might look like. So, having talked a little bit about functional forms, right, now let's, before I get onto this lag stuff, right, so when we're utilizing sort of unconventional, or when we're using standard linear form, right, we want to document our thoughts about why we're doing that. So we want to, when we write up our experiment, right, we want to be documenting why we used a linear form, why we used a semilog form, why we used a polynomial form, what was the rationale for doing so. And then what do the results tell us about whether that was justified or not, or do our results indicate that maybe some additional work needs to be done? Okay. All right. So let's move on to this idea of lagged independent variables, right? So of course, not as it says here, not all results are instantaneous, right? So when X happens, Y doesn't necessarily instantaneously happen. It may be that X happened in the past and it leads to Y happening in the present. Of course, you're kind of seeing we're starting to get into thinking not just about correlation but causality here with this. But let's say that we think that variations or values of the past X variable, so in this case we're going to say x1 t minus 1, we think that actually has an impact on the current variations in Y. Okay, well, we might include our data, right, from the previous period here, regress our previous period X data against our current period Y data. So, maybe if we were saying something like, well, consumption spending in the most recent previous period contributes to incomes in the current period. So then maybe we'd use our consumption data from the previous quarter, like quarter 4, 2019, to explain incomes in first quarter 2020. Okay. Now, when we do that, again, we can't interpret that beta in the same way that we would with the non-lag linear form. In that case, what that beta 1 now is telling us is how movements in this historic value of X impact the value of Y. So they're not about how X impacts Y, they're specifically about how this historic X, not other historic X's, only this t minus 1 X impacts the value of Y. So for example, we could have beta 1 x1 t minus 1, beta 2 x1 t minus 2, beta 3 x1 t minus 3, and so on. So we could run several different lag periods against Y, and then our estimated beta associated with each of those is going to tell us how variations in the X variable in that period are impacting Y. Okay, right? So we should expect some variation in those estimated betas, because it's likely that those lagged impacts aren't constant. Okay, now again, this is going to introduce multicollinearity into that is, all the x1s are going to be correlated with each other, right? Okay, of course. Unless it's a random walk, right? Okay, unless sort of x1 bounces around totally randomly, right? But if x1 has any kind of pattern over time, then we're going to introduce that multicollinearity. All right, so the third thing then is this idea of slope dummy variables. Now, we've talked about dummy variables in the past as intercept adjusters, right? So we essentially allow the intercept to adjust for varying conditions. And in class we talked about how we might use that to adjust for like different months, right? Because in wintertime maybe people buy less unless it's like the holiday season, and then in summertime maybe people buy more, right? And so that's a shifter of a demand curve, and so we want to eliminate or mitigate those variations from our estimated relationship. But we may also want to adjust the slope, right? So we may want to adjust the slope of, say, like a demand curve or a supply curve or any number of other things, right? And in that case, we can use dummy variables in this sort of manner that we see here. So where D represents a dummy variable, and then we have our intercept, right? Our beta 0, our constant term. Then we have our variable x1, right? Then we have our sort of normal style dummy that we've done before, where it's an intercept type relationship. Our estimated beta 3 here. and then the value of our x times dummy, right? And so what we're going to get then is if dummy variable equals 0, right, then what's going to happen, right, is this drops out and this drops out, and right, these become 0. This whole chunk here becomes 0, and then the change in y with respect to a change in x is beta 1, or this one right here. Okay, right, and if the dummy is 1, then what happens is this turns on, right, but our change in y with respect to a change in x now becomes the sum of this and this, right? So essentially I mean, it could be positive or negative, right? But let's just start with the simple idea that it's positive, right? Then our impact of movements in our x variable on our y variable can be interpreted in our regression results as being the sum of the estimated coefficient here, beta 1, and beta 3 here. There are, of course, problems associated with incorrect functional forms, and it's impossible to know the true functional form, right? For a lot of reasons that we've already talked about. But where we start with this is with the literature, right? So everybody sort of watching this is new researchers and new to econometrics, right? So for us, right, we want to see what other people have done. What are the forms that they've used? In some cases, you're going to find that there is no sort of one right answer, right? In fact, that's going to happen a lot. And so then it may make sense to start testing different functional forms. And we kind of talked a little bit about that earlier in this one, but that the test of functional forms is something we'll get into a little later in this term, at least a little more than this, but it can get quite sophisticated and well beyond the scope of this course. And so again, at this level, you want to start to be aware of this issue, right? Aware that there are different functional forms that are appropriate in different environments, and you also want to be aware that one should consult the literature, and then you also want to be aware of some of the interpretation of the estimated betas associated with those different functional forms. So if we have any reason to believe that the functional form is faulty, then we should be very hesitant or modest in interpreting our estimated betas in those regression equations. Okay, well, that's the end of this lecture. In the next lecture, we'll be talking about multicollinearity, which we've talked about a lot already. It's really hard to avoid talking about multicollinearity in these things, but I hope you're still hanging in there, everybody. Again, there'll be a companion video to this where I sort of do this and show you these different functional forms, and we go through and interpret the estimated regression outputs. Hope to see you there. Hope everybody's still having fun. I know I am, right? Really I am. So this is great. Okay, thanks everybody. Bye.